We are Group 14, and we are presenting on zinc. My name is Parker Wilson.
I'm Jack Kamen. By the end of today, you're going to learn why zinc is the unlikely hero of structural materials.
So, zinc as a material wasn't recognized until more modern times, but it had been used in brass and started to be produced in large quantities by 1400 BCE. Zinc was first isolated in India during the 14th century CE. And the reason this took so long was because zinc is historically hard to obtain in large quantities due to having a boiling point of 907 degrees Celsius. But generally, a reduction reaction with zinc oxide and carbon or charcoal um, needs to occur at temperatures well above 1000 degrees Celsius, which at that point, zinc will have been turned to a vapor, and only small quantities of zinc were able to be obtained before processes were refined enough to obtain larger quantities. When zinc was condensed in the chimneys of smelters.
All right, so for the physical properties of zinc, the reason I say it's the unlikely hero of structural materials is because it's kind of not that good structurally. It's like aluminum, but all the bad things are worse. Um, it's an HCP metal, so normally it wouldn't be ductile, but its melting point is 420 degrees. So at room temperature, it's like you're hot working it. And it has an elastic modulus of just about like aluminum at 70 gigapascals, but its thermal expansion coefficient is twice that of aluminum. Um, and actually it's the unit cell, it's HCP, and it's really anisotropic, so it actually expands 6 times more in one direction than any other, which is pretty bad. And for that reason, maybe unsurprisingly, it's less than $1 per kilogram. And actually the textbook opens up with a quote by this guy on the right, SWK Morgan, who worked in the zinc refining industry, saying zinc is not a glamorous metal. And he's right. It looks kind of bad, but it has a lot of really cool uses. So one of the important properties about pure zinc is interesting reactivity. And Parker's going to talk about this a little bit later too, but most of its uses have to do with corrosion resistance. It's a really strong reducing agent, so it really wants to oxidize. But actually, when you have it in an outdoor environment, it doesn't just form an oxide layer. Um, it forms a thin oxide layer, but it also forms a hydroxide layer in moisture, and in a CO2 atmosphere, it forms a carbonate, which is water insoluble, which and all of those in combination make it really good at resisting corrosion in weather, which is why they use it um, as a coating in like tin roofs and light poles and handrails and everything outside. So where do you actually get zinc? Well, the main source of zinc is in zinc sulfide or zinc blend, and for my ceramics people, that's where the structure gets its name from this zinc blend. And so the first thing they do is they roast it at a high temperature in an oxidizing atmosphere to just swap out the sulfur for an oxide. And they actually keep that they keep that sulfur oxide because later on in the process, they turn it into hydrosulfuric acid. But after that, once they have zinc oxide, they can either do pyrometallurgy, where they have it at a high temperature in a reducing environment with either carbon or carbon monoxide that reduces it and produces carbon dioxide, or they put it in an acidic solution um, with the sulfuric acid and run a current through it, and then it plates on the cathode.
Now we're going to transition into the applications of zinc. One of the major applications of zinc is galvanization. Galvanization is a process of protecting typically steel against corrosion. How it works is the zinc coating is bonded by means of um, intermetallic interface, where the zinc coating forms a couple of different intermetallic comp- compounds between um, iron and zinc, with varying percentages, varying from the pure zinc coating all the way to the pure iron slash steel material the coating is covering. Um, and type of protection offers two um, mechanisms of protection. The first is barrier protection. This one's a little bit obvious. The zinc coating physically provides a barrier against corrosion causing agents. So if the zinc is covering the iron, no water or water vapor can get down to the iron, which would corrode it. The second, which is actually even more effective and cool, I think, is the galvanic or cathodic protection method. And how it works is the higher electronegativity of zinc attracts corrosion away from the adjacent steel. So essentially, a reaction happens where any corrosion causing agents has to corrode the zinc first before it can even start corroding the steel. So even cracks in the zinc coating would not be enough to cause corrosion of the steel. This is an advantage of zinc coatings versus like just a regular barrier protection like paint on steel.
Another application for zinc is alloying other metals. And one of the largest ones is brass, which is copper with between 20 and 45% zinc. And at lower zincs, like zinc percentages, it provides solid solution strengthening, which can actually triple the yield strength of copper because it's pretty soft, just pure copper. But when you add more zinc, it can include a BCC phase, uh, and there's a picture of that over on the right. And there's also at really high zinc levels, there's naval brass, which is has really good corrosion resistance, and so they actually use it submerged underwater. But Uses for brass uh, also include low coefficient of friction applications, uh, like moving mechanical components. So that's why they use it in musical instruments. Because if you have a trumpet, you're blowing moist air through it, and you're moving the valves, and you don't want it to last like half a year. So they make it out of brass. So although there aren't a whole lot of uses for zinc alloys, um, its low melting point is useful. So zinc and zinc alloys are good for die casting since they have really low viscosity. And in die casting, you have a molten metal like this picture over here, and you press down on it, use the pressure to push it up into a die where it can cool really fast. And that's nice because you can do it really really fast, which makes production cheaper. And although its physical properties aren't that good, you can make them better by adding aluminum and copper just for solid solution strengthening. Um, so they don't use die cast zinc alloys for structural like load bearing things. Mostly it's for decorative, like little decorative things like you might have on a car. But also something a little bit interesting. 22% aluminum in zinc behaves super plastically, which I thought was kind of cool. Another really cool use for zinc oxide actually is in electronics. So it's used to make varistors, which is kind of shorthand for voltage dependent resistors. Um, and specifically, they're really resistive at low voltages, but then they have a really steep slope in their breakdown region, and they just start conducting. And this comes from the structure of it. In the lower left, there's a picture of the microstructure of this. Um, and the reason it acts like that is because it's only the only conduction mechanisms it can have for electrons across those grains is through the intergranular layer, which is tunneling and thermionic emission, like in an SEM needle. But those both require really, really high fields. But once it starts conducting like that, it conducts a lot, once you have enough field. So those little grains are sintered zinc oxide particles, and the layer between them is a mixture between zinc oxide and SB203, which is also an additive to inhibit grain growth, so they can actually tune the size of the grains and the breakdown voltage, and it stays like that. The grains don't grow and it changes over time. But the main use for these is to protect fine circuitry, because you don't want to design a circuit for a, a voltage spike of 300 volts for a you want to protect it with one of these. Um, so you would put this in between the supply and ground, so that if there's a huge voltage spike in the supply, it all conducts through this instead of going through the fine circuitry.
An additional use of zinc in electronics includes batteries. Alkaline batteries, in particular, function with an electrochemical reaction between a powdered zinc anode with a manganese dioxide carbon cathode, generating electricity. Zinc is used in these batteries because of a good combination of higher standard electric potential. They have a chemistry that is easy to work with when manufacturing them, in comparison to lithium ion batteries, for example. Zinc is utilized quite commonly in biological functions. In fact, it is used by over 300 enzymes in humans. Recently, protein domains called zinc fingers have been used in part of the design of a class of engineered proteins called zinc finger nuclease, or ZNF. ZNF technology has a potentially life saving application in the realm of gene editing. Researchers in one study used ZNF technology as a potential treatment for HIV. In their study, researchers modified the genome of a patient's T cells to make them more resistant to the virus. So, pure zinc as a material has generally poor structural properties, but it has good corrosion resistance, and this allows it to be used for coat actual structural materials for outdoor use in environments that generally aren't kind to them.
And zinc aluminum alloys are also used for die casting because they have such low viscosity. And zinc is also used to alloy copper to use brass, and everyone knows about brass. Um, Zinc oxide is used in a lot of electronics in varistors specifically, and zinc also is in zinc fingers, which are used for protein engineering.
So here are our references. Thanks for listening to our presentation. We hope you enjoyed it. Once again, I'm Parker Wilson.
I'm Jack Kamen. Does anyone have any questions?